meter is pushed down with a velocity 0.01 meter per second towards a wall, resulting in the drainage of the fluid between the plate and the wall as shown in the figure. Assume two-dimensional incompressible flow and the plate remains parallel to the wall. The average velocity of the fluid in meter per second draining out at the instant shown in the figure in meter per second, corrected to 3 decimal places. So the diagram of the problem is given here. We can see here this is the wall, the bottom one is the wall and the top one is the flat plate. Okay, and the flat plate is at distance 0.1 meter as shown here. The width of the wall, now if we draw the side view of this diagram, let's draw the side view, or let's draw the isometric view here. Now here, suppose this is the flat plate of length L. So the length of this flat plate is L, that's given in the problem, and this is the wall. This is the wall. And between the wall and the flat plate there are fluid particles. Let's say the arrangement of fluid particles are something like this. This is just a rough diagram. Okay, something like this. This is the first, these are the layers of fluids. Now when the plate is moving downward with a velocity u, let's say up for the plate velocity, what happens, these fluid particles, it will try to run out from here, okay, from the side. Okay, so, and this height here, it is given in the problem, this height is given and it's given as d, and the width, let's assume the width of this plate be b. Okay, let's say the width is b. Now the rate of mass displaced through this plate when it moves down will be equal to rate of mass displayed by the plate and the wall through both sides, right? So this velocity is given as u average avg. This side also we have to consider the velocity of fluid as v or u avg average. Okay, so we can write here mass of fluid displayed by this plate. So let's say mass flow rate by due to plate should be equal to mass displaced between this plate and this wall. Okay, so let's write mass flow rate between of the fluid. Let's write F. Okay, so we already know here that m dot F represent the mass coming from this cross section. Okay, let's draw this cross section something like this. So whatever the fluid is coming out of this cross section is represented by m dot F, and m dot P is the fluid particles. So these are the fluid particles, right? And these will be this will be getting compressed like this. Not compressed, actually it will be coming down because of the movement of this upper plate, and this is given by m dot P. So this is also the continuity equation. Let's write here continuity equation. Okay, now let's calculate this value. So the rate of mass displaced through the plate will be given by the density of fluid multiplied by the area of the plate. So let's write area of plate multiplied by the velocity of the plate. So let's write up for velocity of plate, and this should be equal to rate of mass displaced between the plate and the wall through both sides. So m dot F will be equal to density of fluid multiplied by the average velocity UAVG multiplied by the cross-sectional area of the side of plate. Okay, so let's see the cross-sectional area. So we are talking here about this cross-section. Okay, this, let's give a name A, B, C and D. So this cross-section we are talking about here. Okay, and since the fluid is moving from both sides of the plate, we will multiply this by 2. Okay, so let's write AF for this cross-sectional area ABCD. Okay, because fluid is going out from here. Now coming back to the calculation, so the density of fluid is same, so we can common out because it's the same fluid present there, Now area of the plate is the width of plate, so length multiplied by the breadth. Let's say B is the breadth of the plate, and UP, that is the velocity of plate, should be equal to U average, that is 2 times of U average, let's write like this, AVG, and area of the cross sectional ABCD, that will be equal to B times the separation between the plate and the wall, that is given by D. Okay, let's see in the diagram. For better understanding, let's see in the diagram. So area ABCD will be given by B into D, because we have assumed BC we have assumed to be B. Therefore the area of the plate, so let's write here area of plate. So this area AP will be equal to the length that is given in the problem L into B. Okay, that's what we have written here. So we can cancel out B from here, and then we can write, so the average velocity of fluid we can write as average velocity will be equal to L into velocity of plate divided by 2 times of D, the separation between plate and the wall. So in the problem the value of L is given, right? So the length of plate is 1 meter multiplied by the velocity of the plate, that is 0.01 meter per second, divided by 2 times of the separation between the plate and the wall, and that is given as 0.1 meter. Okay, so the velocity, average velocity of fluid will be equal to 0.05 meter per second. Now let's go back to the problem and match with the given options. So this is a fill in the blank type question. So let's fill in the blank. The average velocity of the fluid in meter per second draining out at the instant shown in the figure, that means this velocity U average, how much we have calculated it? 0.05 meter per second. Okay, and it's written correct to 3 decimal place, so we can write here 50. To know more, you can refer to the NPTEL course lecture number 19, Gauti Flow, by Professor Suman Chakraborty of the Department of Mechanical Engineering at IIT Kharagpur.